This is Module 3, Oxygen Binding Proteins and Methods for Analyzing Proteins. In this video, I'm going to be discussing hemoglobin, which is the primary oxygen transport molecule in the body. And I'll also be comparing its binding affinity for oxygen to that of myoglobin. So in the last video, in video 3-1, I talked about myoglobin and how it is responsible for storing oxygen in the body. Hemoglobin is another one of the oxygen binding proteins in your body, and it's responsible for transport. This is one of the cooler proteins that I'll discuss in this class. Hemoglobin is exactly structured for its function of catch and release. So that's going to come back. We're going to come back to this idea of catch and release when we look at the binding curves. But let's first look at the structure of hemoglobin. Hemoglobin is a multi-subunit globular protein. So it is a globular protein, just like myoglobin, but it has 4 separate subunits. So therefore, because it has 4 separate subunits, it's referred to as a heterotetramer. It has 2 alpha subunits and 2 beta subunits. So the 2 alpha subunits would be in red, the 2 beta subunits would be in blue. This means that 2 different genes encode for these proteins, an alpha hemoglobin gene and a beta hemoglobin gene. And then those genes are transcribed multiple times so that you can get multiple copies of each of those genes, multiple copies of each of those proteins. Once those 4 individual proteins are created, they'll fold into their secondary, which is a bunch of alpha helices, and then their tertiary forms, which is alpha helices clustering together to form a globular protein. Once those tertiary forms are finished folding, they come together in this quaternary structure where you see the 4 separate distinct subunits clustering together by non-covalent interactions. Each globin subunit has its own heme group, and so here we see that heme group popping up again. For a review on the structure of what heme is and what the structure is, look at video 3-1, myoglobin. The function of hemoglobin is to carry oxygen in the blood from the lungs to the tissue. So it has to be able to bind oxygen in the lungs, carry it to the tissue, and then release oxygen once it gets to the tissue. It actually has a couple of other rules too, which I'll discuss towards the end of this video. So let's take a look at the hemoglobin binding curve for oxygen. So here's our oxygen binding curve. This is myoglobin. This is what we looked at in video 3-1. And I have changed the units for the partial pressure of oxygen have changed to torr in this video. But the hyperbolic curve looks the same on this with this new measurement. And so what we see here is that the P50, or the substrate concentration at which half of the myoglobin molecules are bound, is 2.5 torr. So that's the P50 for myoglobin. The P50 for hemoglobin, however, is much higher. It's about 26 torr. So it takes 26 torr amounts of oxygen to bind half of the available hemoglobins in solution. So if you want hemoglobin to bind like it binds, if you want oxygen to bind hemoglobin like it binds to myoglobin, you have to increase the amount of oxygen in the system. So basically overload the system with oxygen, and that will force hemoglobin to bump into it, bind to it, and hang on to it. The difference in the shape of the curve has to do with the structure of the proteins and also how many oxygens it's capable of binding. The structure of myoglobin is one heme group, one molecule can bind to it. So that makes it well suited for storage because it binds to it very tightly in a very low concentration of oxygen and will hang on to that and will not let go. Even if the oxygen concentration drops in the tissue, it's going to take a very, very small concentration of oxygen to encourage myoglobin to release its oxygen molecule. The structure of hemoglobin, however, makes it well suited for transport. It catches oxygen in the lungs where oxygen concentration is very high, and therefore hemoglobin is saturated. But when oxygen concentration drops to a low concentration as is present in the tissues, fewer hemoglobin molecules will be bound to it. Fewer oxygen molecules will be bound to hemoglobin. So again, it takes about 26 torr for only 50% of the hemoglobins to be bound to oxygen. The other 50% are open and free of oxygen binding. In the lungs, however, oxygen concentration is so high that all of the hemoglobin present in the lungs will be saturated with oxygen. So this makes it really well suited for catching oxygen in the lungs, right? There's so much oxygen in the lungs that all of the hemoglobins become bound to oxygen. When oxygen concentration drops as it moves to the tissue, some of that oxygen is going to fall off of the hemoglobin, and then it won't be able to bind it again once it falls off because there's not as much of it around to encourage that. So which has the higher affinity for binding oxygen? Myoglobin does, because its P50 is much lower than the P50 for hemoglobin. You might have noticed that hemoglobin's oxygen binding curve is sigmoidal, and this is due to a phenomenon called cooperative binding. At a low oxygen concentration, hemoglobin has a hard time binding that first oxygen. This is a reversible binding event. So oxygen becomes bound to hemoglobin, but it also can fall off. It's reversible. The interactions that hold them together are non-covalent interactions, and so it can fall off fairly easily. If hemoglobin is in an environment where oxygen concentration is very high, and it happens to lose the oxygen that it's bound to, very quickly it will rebind another one because there's so much oxygen around and lots of opportunity for hemoglobin to bump into an oxygen molecule. However, when there's a low amount of oxygen present and hemoglobin loses its oxygen, it's very difficult for it to rebind. There's not as much oxygen around, and then also there's this phenomenon of cooperative binding. At very low oxygen concentration, hemoglobin has a tough time binding that first oxygen. The position of the heme group is the reason why, and I'm going to come back to that in a little bit. So where would this be difficult to achieve? Where is oxygen concentration low? Well, it's low in the tissue, and so it would be difficult for hemoglobin to bind oxygen when it is in the tissue. That's a good thing. You don't want hemoglobin to be irreversibly bound to oxygen in the tissue, or to be bound with very high affinity in the tissue, because the goal is to bring oxygen to the tissue and let go of it. Where is oxygen high? It's very high in the lungs. And so when hemoglobin is present in the lungs, it's much easier to bind that first oxygen, which is exactly what you want to happen. You want hemoglobin to bind oxygen in the lungs and then move it to other areas of the body. So at higher oxygen concentration, binding of the first oxygen causes a conformational change in the subunits that surround that first one. Remember, hemoglobin is a 4 subunit molecule. And so when that first oxygen binds to the first subunit, it causes the neighboring 2 subunits to kind of shift and adjust their form a little bit. This actually makes the heme group more accessible to binding to oxygen, and then binding oxygen to the second and third subunits is much easier to accomplish. Once that happens and binding to the second and third subunits is complete, that fourth subunit will bind oxygen with 100 times the affinity as when the first oxygen bound to the first subunit. So every time an oxygen molecule binds to a subunit in a single protein of hemoglobin, that makes it easier for the neighboring subunits to bind, and it does so more quickly. And so binding oxygen increases the affinity for binding more oxygen, and this is referred to as cooperative binding. So let me show you the sigmoidal curve. That is why initially the binding of oxygen to hemoglobin, its slope is a little flatter, but as you increase the amount of oxygen, in the system, it will encourage hemoglobin to bind to them more. And then after the first binding event occurs, that encourages oxygen to bind to the neighboring subunits at a faster rate. And so the slope of the line gets a little steeper up here where oxygen concentration is a little bit higher. That first oxygen is probably already bound, and it's making it easier for the second and third oxygens to bind. And then, of course, the fourth one will bind at the highest affinity. And so the slope of the line is slow, flatter initially, and then becomes steeper, faster as oxygen concentration increases. That illustrates cooperative binding. So let's take a look at the position of the heme group when this is happening. The cooperative binding of hemoglobin occurs due to an oxygen-induced change in the structure. So remember that first oxygen molecule, when it binds to the first heme group, that's going to cause changes in the neighboring subunits. So let's make sure we understand that there's 1, 2, 3, 4 different places where oxygen can be bound. When hemoglobin is not bound to any oxygen, it's referred to as deoxyhemoglobin, no oxygen bound to this hemoglobin. It's also referred to as the T state or the tense state, where the heme group is not as accessible to so this heme group is not as accessible for binding oxygen. It's more buried and clustered in the center of the globular protein. It can bind oxygen. It just takes a lot of oxygen around in the system to encourage that interaction to happen. And so if you increase the amount of oxygen in the system, it sort of can't help it. It will find a way to bump into that group and bind it. When there is oxygen bound to hemoglobin, this is referred to as the R state or the relaxed state. And that's when the neighboring subunits will kind of shift and change in response to the first oxygen binding event. And what happens is it repositions that heme group in a more favorable position for binding oxygen. So R state is the relaxed state. The subunits aren't as tightly bound together. Because that first oxygen binding event has loosened the neighboring subunits, the tightness of the neighboring subunits. The T state is considered the tense state because that's when most of the heme groups are buried towards the center of their subunit. So let's take a little bit of a look again at the binding site. So, okay, so here is the hemoglobin, 2 hemoglobin subunits next to each other. This is the binding site, and this is sort of an unstable part of the hemoglobin protein that sort of is able to move around a lot more. Okay. When deoxyhemoglobin is in the T or tense conformation, it's reluctant to bind that first oxygen. It's unfavorable because that porphyrin heme group is closer to being buried in the center, and oxygen can't access its binding site. When one molecule of oxygen binds to the iron in the heme group, that actually makes this a little bit more stable. And so it's sort of, this is actually the part of the molecule that's attached to that histidine residue. And it comes and sort of stabilizes the oxygen being bound to the receptor. When this happens, the tetramer changes conformation from T to R. The iron moves towards the center of the porphyrin ring as opposed to being buried. Sorry, let me restart that thought. I apologize for some of the noise interruptions. It's very chilly in my house, so I'm trying to record outside in the sun, and it's not going well. There's a lot of noise interruptions. So this will be the last video I record outside. So anyway, let's make sure we understand this. Again, oxygen binding to individual subunits of hemoglobin alters the affinity for oxygen in adjacent subunits. When oxygen is not bound to anything, those heme groups are buried in the center, and this is of the monomer of the subunit. When oxygen binds to the iron complex, so the iron in the center of the heme group, it causes the iron atom to move back towards the center of the plane of the porphyrin ring. which positions it in the ring to be more accessible to oxygen. At the same time, remember that histidine residue, that the heme group is attached to? The R group of that histidine residue is pulled towards the center of the porphyrin ring also. This interaction forces the plane of the ring sideways towards the outside of the tetramer, and this induces a strain in the protein helix. So when the histidine moves, it introduces steric hindrance and strain in the helix that it's attached to. So this strain is transmitted to the remaining 3 subunits in the tetramer, where it induces a similar conformational change in their heme sites to position the heme groups to be more accessible for binding oxygen. So when 1 or 2 molecules of oxygen bind to the iron, the tetramer will change its conformation from T to R as iron moves towards the center of the ring, and the R group of histidine is pulled back towards the porphyrin ring. This induces that strain in that subunit and also forces the neighboring subunit to become more stable. And so this unstable portion of the subunit becomes more stable and is easier to, and it's better able to stabilize iron once it binds to that heme ring. So subsequent oxygen bind readily because hemoglobin is in the R state, and those iron molecules in the heme groups are positioned more towards the outside of the tetramer, making them more accessible to oxygen. What's really interesting about this molecule is that when oxygen can bind cooperatively to hemoglobin, it can also release in the same way, where once one oxygen molecule becomes released from one of the subunits, its conformational change will move back to the T state, and that forces neighboring subunits to also drop their oxygen and move back to their T state. So oxyhemoglobin retains their bound oxygen in the lungs where oxygen pressure is really high, but when hemoglobin moves towards the tissues, that means oxygen concentration is dropping. And so again, if hemoglobin accidentally releases one of its oxygen, the R state will slowly convert to the T state and make it less able to bind any oxygen in the surrounding area. And then also in the surrounding area, oxygen concentration is low, which drops the likelihood that an oxygen molecule will actually bump into a hemoglobin long enough for it to bind to it. And so these binding characteristics are critical for hemoglobin being a catch and release molecule. In the lungs, oxygen concentration is high, and 95% of the hemoglobins present in the lungs are saturated. Cooperative binding increases their affinity for binding oxygen and helps to saturate hemoglobin when concentration of oxygen is so high. So we have 2 things working to encourage hemoglobin to bind oxygen. The first is the cooperative binding features of the molecule, and the second is the high oxygen concentration in the lung. In the tissue, oxygen concentration drops, and that's when you see that hemoglobin is only 55% saturated. This is due to another 2 similar things. One, when oxygen falls off that first subunit, it causes the hemoglobin to move back into the 10th state, and all of the neighboring subunits will be more likely to drop their oxygen, their bound oxygen. And then 2, oxygen concentration in the tissues is fairly low compared to the lungs, and so there's less likely of a chance for that oxygen to bump into hemoglobin and actually bind to it. And the hemoglobin's in a bad state for binding oxygen. So the binding of oxygen to hemoglobin is 4 different binding events that are in equilibrium with each other. And the equilibrium of oxygen binding is affected by the oxygen concentration in the tissues or in the lungs. So when there's high oxygen concentration, equilibrium will shift to the right, where all 4 of the hemoglobin monomers or subunits are bound to an oxygen molecule. As oxygen concentration drops, so if oxygen concentration is low on this side, that shifts the equilibrium back towards this end of the equation, where hemoglobin is not bound to oxygen. So again, when when oxygen concentration is high and this increases, we push the stepwise binding events to this direction. When oxygen concentration drops and is low on this end, that means we're going to push the stepwise progression of losing oxygen towards the left side of the equilibrium equation. So where does myoglobin come in? Myoglobin has a really important role here too. And so let's follow the stepwise process of binding oxygen into the lung, delivering it to the tissue, and then storing it in the tissue. So we're going to stitch together this idea of oxygen binding molecules, a transport molecule, which is hemoglobin, to the storage molecule, which is myoglobin. Okay, so in the lung, hemoglobin has a high affinity for binding oxygen because oxygen concentration is high in the lung. And then also, once that first oxygen binds to hemoglobin, that's going to encourage all the three remaining subunits to bind oxygen. And so hemoglobin goes from deoxyhemoglobin to oxyhemoglobin. Oxyhemoglobin is now saturated with oxygen and it enters the bloodstream and travels to the muscle tissue. And remember, muscle tissue has a lower oxygen concentration. Oxygen binding to hemoglobin is a reversible event. And so by chance, that oxygen molecule could come off. Once that first molecule comes off, the remaining subunits in that hemoglobin molecule are encouraged to drop their oxygen as well. And then because hemoglobin has a low affinity for binding oxygen when oxygen concentration is low, it is unlikely to pick back up that oxygen molecule. Complicating matters for hemoglobin is the presence of myoglobin, which has a very high affinity for oxygen, even when oxygen concentration is low. And so the moment that hemoglobin loses that first oxygen, myoglobin is already there, ready to grab it up and store it. And then once hemoglobin loses its remaining oxygens again, that hemoglobin is in its 10th state, so it's not really optimal for binding oxygen. Concentration of oxygen is low, so it's less likely to bump into hemoglobin. And the presence of myoglobin pretty much ensures that any dropped oxygen is going to get picked up by myoglobin and stored in the tissue. Myoglobin here will release its oxygen only when cellular respiration requires its use. Oxyhemoglobin returns to its deoxyhemoglobin state and then travels back to the lungs via the bloodstream to repeat the process. I mentioned at the beginning of this video that hemoglobin has additional functions as well. It's not just able to transport oxygen, it's also able to transport waste products like carbon dioxide and hydrogen ions. This is critically important. Hemoglobin is headed back to the lungs, where things like carbon dioxide are released as waste products. Think back to the bicarbonate buffering system, where we release carbon dioxide as a waste product by exhaling air. So if hemoglobin is going to travel back to the lungs as an empty molecule, it may as well take out the trash while it's on its way back to the lungs, right? And so let's look and see where these two things are binding. Hydrogen ions, if you'll remember, are a common waste product of cellular respiration. So there's going to be lots of hydrogen ions in the muscle tissue where there's or in tissue in general, where there's lots of cellular respiration. Hydrogen ions will bind to many different amino acid residues in hemoglobin when hemoglobin is in its tense state. So if it's bound to oxygen, hydrogen ions have a tough time binding to these residues. But in the tissues, when it starts to lose its oxygen, hydrogen ions are better able to bind to the T state. This leads to salt bridge formation between the hydrogen ions and some of the negatively charged or partial negatively charged residues on hemoglobin amino acids. Some of the residues that do this are the histidine residues in the hemoglobin molecule and asparagine residues in the hemoglobin molecule. So here's that proton there. Carbon dioxide actually is capable of binding to the N-terminal group of each globin subunit only when it's in the T state. And so when it's in the 10th state, this N-terminal carbamate, so this N-terminal C group, I'm sorry, this should be the C terminus, not the N terminus. Oh no, no, sorry. This is correct. I was looking at the wrong thing. I apologize. So here's the N-terminus. Here's R. This represents the rest of the hemoglobin molecule. I apologize for that, that error, my mistake. So my original statement was correct, that CO2, which is pictured here, binds to the N-terminal group of each globin subunit. So there's a free amino group at the N-terminus of each of the 4 subunits of hemoglobin. It can associate with that carbon dioxide via a covalent interaction and form a carbamate molecule. So we call this carbaminohemoglobin. And so hemoglobin is capable of transporting 4 oxygen molecules because there are 4 subunits. It's also capable of transporting 4 carbon dioxide molecules and bringing them back to the lung. When the hydrogen ions and the carbon dioxide molecules are both bound, that actually stabilizes the T state by increasing the non-covalent interactions that keep that protein tightly wound up. And so these 2 molecules further stabilize the tense state, or the inability to bind oxygen, and that is yet another contributing factor to why hemoglobin has a tough time hanging on to oxygen in the tissues. This also means that binding of hydrogen ions and carbon dioxide is inversely proportional to the binding of oxygen. And so if there's a higher concentration of hydrogen ions and carbon dioxide, they will bind more readily and stabilize the T state, and then it's therefore not capable of binding oxygen anymore. Where there's less of a hydrogen ion concentration and carbon dioxide concentration, so in the lungs, where carbon dioxide is constantly being expelled, that actually destabilizes the tense state, making hemoglobin more able to bind oxygen, since the non-covalent interactions within the protein are a little looser when there's less hydrogen ions and less carbon dioxide bound to it. Okay, so in tissue, again, cellular respiration leads to the consumption of oxygen, so oxygen concentration is low, and the release of carbon dioxide, so carbon dioxide concentration is high. Remember, when that happens and carbon dioxide is in high concentration, that means this side of the bicarbonate buffering equation is higher in concentration than this side. And so that will encourage the carbon dioxide and water in tissue to combine to make carbonic acid. And that is that's going to push for the formation of bicarbonate and hydrogen ions. This means hydrogen ions are going to increase, not just as a byproduct of metabolism, but as a byproduct of just releasing carbon dioxide into the bloodstream. That also increases hydrogen ions. And so if hydrogen ions increase, that means your pH is dropping. So pH is related to the ability of, pH is related to oxygen transport in the body. At a high hydrogen ion concentration and a high CO2 concentration, binding to hemoglobin again stabilizes the T state and reduces affinity for oxygen binding, and oxygen falls off, and is more further encouraged to fall off. In the lungs, carbon dioxide is exhaled, and so now we're in the lungs here. This equation is what's happening in the tissue. Now this equation is changed. The direction of the arrows change when we're in the lungs. CO2 concentration in the lung is very, very low. That means this side of the equation is going to be high, and that will encourage bicarbonate to bind to hydrogen ions and push the reaction in this direction. And so hydrogen ions will decrease and pH will increase in the lung. So this means that at a low hydrogen ion and low carbon dioxide concentrations, there are fewer opportunities for H and CO2 to bind to hemoglobin. So hemoglobin's tense state is destabilized, which increases its ability and its chances of binding oxygen and hanging onto it. And so pH is related to hydrogen ion concentration, which is related to the bicarbonate buffering system, which is related to carbon dioxide as a waste product, and that is affecting the ability of hemoglobin to do its job. And so the bicarbonate buffering system is very closely related and interacts with the ability of hemoglobin to transport oxygen.